Good morning. My name is Luke DeCruz, and this is my online submission for the first prelim of MAE 5540. Today, I will be discussing the rocket equation, its derivation, and its mission implications. We begin with a brief introduction to rockets. A rocket is an object that consumes propellant in order to accelerate. The ejection of the propellant from the rocket produces thrust, which pushes the rocket in the opposite direction of the ejected propellant. Note that a rocket's mass is not constant if the rocket is accelerating under its own power. As the rocket burns propellant, it loses mass through its exhaust plume. For this reason, we cannot calculate a rocket's thrust by only using the standard F equals ma equation. Instead, the rocket equation uses the conservation of momentum principle to relate a rocket's velocity to its mass. Our scenario is the ideal case, so we only consider the rocket's thrust, which, as mentioned earlier, is provided by the propellant ejected from the rocket. We assume a perfect vacuum, ignoring atmospheric effects such as lift and drag. Now for some historical context behind the rocket equation. The Russian scientist Konstantin Tsiolkovsky, pictured left, is credited with being the first to derive the rocket equation in 1903. The equation was independently derived by the American Robert Goddard, pictured middle, in 1912, and by the German Hermann Oberth on the right in 1920. I will now derive the rocket equation using the conservation of momentum principle. First, we establish the terms for our equation. Capital M is the mass of the rocket. Lowercase m is the mass ejected from the rocket. Capital V is the velocity of the rocket relative to a stationary observer. This means that if someone was watching the rocket from afar, this is the velocity that they would register. The fourth term is UE, which is the exhaust speed in the rocket's frame. Note that it is a constant. With the exception of UE, these terms are time dependent. For this derivation, we place the rocket in an arbitrary control volume CV. We start with the conservation of momentum in equation 1. Looking at the control volume, there are two sources of momentum, the rocket itself and the rocket's exhaust plume. This gives us our expression in equation 2. The momentum of the rocket itself is its mass, big M, multiplied by its velocity relative to the stationary observer, big V. The mass ejected from the rocket is a small amount at any given time, and the rate at which it flows is lowercase m dot. The velocity of the plume relative to the stationary observer is big V minus UE. Integrating this over some time t gives us the momentum of the exhaust plume. Expanding as needed, we set the sum of these two momentums equal to 0, in line with the conservation of momentum principle. To solve this equation, we utilize the chain rule to simplify, as seen from equation 5 to equation 6. We know that the mass flow rate of the plume is equal to the change in rocket mass big M with respect to time, but in the opposite direction, hence the negative sign. After using these facts and rearranging our terms, we get the equation seen in equation 9b. Further solving results in integrating both sides between their initial and final values. On the left-hand side, we integrate for rocket velocity, and on the right-hand side, we integrate for rocket mass. Note that the final F subscript is when all the propellant has been used up. Using natural log properties, we find the relation between change in velocity, delta V, and mass of the rocket. We see that E raised to the change in velocity delta V divided by exhaust speed UE is equal to the rocket's initial mass, which includes propellant, divided by the rocket's final mass, which has 0 propellant. The rocket equation has serious implications on spacecraft mission design. We look at equation 13a first. We can calculate delta V based on UE and initial and final rocket mass. Delta V is important for changing a spacecraft's orbit, and therefore helps determine where the spacecraft can go. A good example of this is the Hohmann transfer, which requires the calculation of delta V to move a spacecraft from one orbit to another orbit of a different attitude. Combining this with UE, which is based on the propulsion system and propellant used on the spacecraft, we can determine the propellant we need for a particular mission. From equation 13b, we can determine the mass of propellant in terms of the rocket's final mass mf and delta V and UE. As seen in class, equation 14 is crucial for determining how much propellant is needed to complete impulsive and low-thrust orbital maneuvers. Assuming mf is known and delta V and UE have already been determined, the rocket equation tells us how much propellant the rocket will use to successfully complete such orbital changes. As demonstrated in this presentation, the rocket equation is immensely useful for any spacecraft mission. We discussed the basics behind the rocket equation, derived it from the conservation of momentum principle, and highlighted its implications for spacecraft mission design. This concludes my presentation. Thank you.